aim to do? Think as a cluster of people. That's not going to work because I need hands to it. Let's see. Okay, what Think aims to do and the kinds of strategies that we have adopted to accomplish that dream. And what we would like you to do is to answer the third question, namely, where do you see yourself in that spectrum of things to accomplish student learning? Ultimate aim is student learning. Not all aspects of student learning, some particular aspect of student learning. One question we forgot to ask. After question 3, there should be a question 4. In this case, I'll tell you what the question is, which is, once you place yourself in that spectrum, or there can be many points in the spectrum, what can we do to help you do those things? So it works in both ways. Okay, so if you can give us that feedback, write it down. Yeah. You had a comment, okay. Sometime, when do we want it? Like, by this evening? Yeah.
What was the fourth question again?
Fourth question. Third is, how do you see yourself in that spectrum? What are the places where you can make a contribution? And the fourth question is, in order to do that, in order to do what you think you will be able to do, what kind of help do you need from us? That's it. Okay, so this is yesterday. What I was supposed to have. Was it yesterday? Whichever. What I did actually yesterday was the continuation of reasoning 1, because the last part, speculative deductive reasoning, wasn't sufficiently done in sufficient detail, so we went through those things. And I will go back to the heliocentric, different other aspects of heliocentric theory in a session later. When I don't know when that is going to be, one of these days, before 2016 ends. Okay.
15.
No, before 2000. This time I meant exactly what I said. So what I want to do now is take up 2 kinds of reasoning and defeasible reasoning. These 2 categories cut across the other categories that I mentioned. So for example, you could have defeasible inductive reasoning or non-defeasible inductive reasoning, probabilistic induction and non-probabilistic induction. So this classification is along a different parameter. Again, the classification is not important, but the nature, the structure of reasoning is important. So that we know, this also applies to students, not the classification, but the choice of the type of reasoning and the norms of those modes of reasoning. So let me go back to the classical type of reasoning. Suppose I say all humans have exactly one heart, and I should probably add adult human being, to avoid the possibility, of some infant having no heart or whatever. And then you can say, this is premise 1, and premise 2 is Zeno is human. And therefore you conclude that Zeno has exactly one heart.
Zeno is an adult?
Yes. Zeno is an adult human, it follows that Zeno has exactly one heart. This is classical syllogism of the kind that Aristotle was talking about. This is deductive reasoning. And this is also non-defeasible and non-probabilistic. Suppose I say most humans have 10 fingers. Instead of all, I have changed the quantifier to most. And you can, from that you can conclude, Zeno is, again, an adult human. And now the inference will be slightly different. The inference will be Zeno is most likely to have 10 fingers. So there's a connection between this and this. What it means is, here in every case in the population of humanity, every member has exactly one heart. Here, you're not saying that it's true about every member of the population. Saying majority of whatever, some word. And so that means we are not completely certain that Zeno has exactly one heart. It is 10 fingers. It is possible that Zeno has 11 fingers. Why is this important? Because in this case, in the case of classical deduction, by classical deduction I mean this. Classical deduction is the Aristotelian type reasoning, which is non-defeasible, non-probabilistic. If you find one human being, exactly even one human being who has 2 hearts or 3 hearts or no heart, this statement is false. In contrast, here, if you find one human being with 11 fingers, this proposition is not false. This is not a case of exception. This is very important. In the formulation itself specifies the probability, therefore this is not an exception. So if you find that the law that you formulate has some what looks like exceptions, then change the law instead of saying exception. Okay, the question would be, yes, it is true that if you find one human being with 11 hearts, it is not, the statement is still true.
Fingers.
Pardon me?
11 fingers, sorry.
11 fingers, what did I say? Okay, I'm sorry. Whenever I say... however, suppose you found in a large random sample of humans, 99% has 11 fingers. Obviously that is false. What if it is 98%? What if it is 97%? At what stage will you say the proposition is false? So what is it, the question that I'm raising is, what does it mean to say most?
How do you define most?
Right? 50% I think you will say the statement is false. So it is more than 50%, but not 100%. Now, in academic inquiry, one of the important conditions is when you make an assertion, you have to specify under what conditions your assertion will be false. If you don't specify this, somebody else would not know how to prove you wrong, and this is important. So if I say something like, when I say most, I mean something like a range of 70 to 80%. People vary in their meanings of the word most. So what is most for me is not most for you, so it is important. If I make an assertion using this, then I have to specify what it means. And this is like the earlier case of the range of inexactness. The whole purpose of specifying the range of inexactness, when I say my height is 5'6" plus or minus 1, what I'm saying is, if the number goes beyond that range, what I'm saying is wrong. I have to say exactly the same thing here.
There's no AC.
Is there, the AC is not working this. When the AC is not working, my brain is not functioning. Okay, so, yeah.
I would prefer to say more than 70% because there will be also above 80% possibility. Like if when we say 70 to 80%.
Ah, okay.
Yeah, so
Sorry,
above 70.
what I meant to say is approximately this range. This is the dividing line.
Okay, so more than this, more than 70
Yeah,
to
yeah,
80%.
in that range. I want to draw a line, right, is what I cannot draw that line with any degree of precision.
Yes.
So that line has this fuzziness.
Yeah.
So this is like saying that object is red, not orange. Under what conditions would I be false? There's an intermediate gray area when I'm not sure. And this is an example of probabilistic deductive reasoning. This is reasoning from population to sample, but in this case it is non-probabilistic, this is probabilistic. Now, instead of using the quantifier most, I could have said with greater precision, I could have said 82% of humans have 11 fingers. Now it is clearer what would make it false. I mean, it's the degree of precision is much greater here. But you may not be in a position to state that in many cases because you haven't actually done the counting. In which case you state it in less precise terms. So if you do that, this will be quantitative probabilistic logic, and this is qualitative probabilistic logic. You can get a great deal of information on this from probability theory. Probability theory, statistics combined together. Probability theory tells you how to move from here to here. Statistics tells you how to move from here to here, from sample to population. Yeah.
So if we know that it's 82%,
Yeah.
and we say 82% humans have 10 fingers,
Uh-huh.
Zeno is an adult human, therefore Zeno is most likely to have 10 fingers. Because we are using the most likely there, it's still probabilistic. We don't know
What is your, are you using the qualitative reasoning or the quantitative reasoning?
So if I put an 82% instead of the
Yeah,
most,
quantitative.
so then
Then
the
you will
last
say-
line still reads as Zeno is most likely.
Zeno is an adult human.
Yes.
Then the conclusion will be the probability of Zeno having 10 fingers would be 82% or 0.8.
Okay, so
You-
it's probabilistic because we still don't know which category Zeno would fall into, but most likely he's in the 82%,
Yeah.
therefore it's probabilistic.
Yeah, the most likely is quantified now, right? And then, the normal specifications of probability, all those things would apply. Yeah.
Small point is that we don't need to say in the second example adult human.
Rakesh, this is speaking.
Yeah, even I had something laughing.
Okay.
Yeah, so I was just, a small point is in the second example, we don't need to say adult human, we can just say human.
Yeah.
Which one? No, you don't want to include, let's say, newborn babes or sort of babes who are not born yet. For example, let's take something like twins. Whether you want to include adult or not doesn't really matter for my purposes.
Okay.
I'm just reminded of the case of Jodie and Mary, where these were two humans
Right.
joined together with one. They had only one heart between them.
Okay.
And of course, had they continued, they would have died.
But fingers,
Oh, I'm sorry. Yes, I'm sorry. Yeah.
okay.
Yeah. Oh, I just continued the same thing over here. You don't need adult for that. Of course, somebody will ask what if fingers are cut off and that kind of stuff. It doesn't matter.
But then he's more likely if he's adult, not
Yeah.
human.
And you may also have to say most human beings who haven't had accidents with their fingers, blah, blah, blah.
Yeah.
Those details don't really matter. I'm just illustrating the point in the sense, the nature of the difference between the two kinds of reasoning. Okay.
So if we turn around, say Zeno has 10 fingers,
Hmm.
then how will it be? Most humans have 10 fingers.
Most humans have 10 fingers, Zeno has 10 fingers.
10 fingers.
So that's not a problem. So
Because
what
if
we are
it's in the
investigating is
category
under
of
what
80 to
conditions
20
would the major proposition be false.
Therefore is,
There are also probabilistic values.
But there also,
that is what you want.
Which one?
most humans have 10 fingers, Zeno has 10 fingers,
Yeah, then it.
so then Zeno is most likely.
Oh, I see. You're talking about.
The other way around.
Okay. So if you begin here, and then you say Zeno has 10 fingers, can you then conclude that Zeno is human? Okay, hold on. Ask Madhav how to do that. All right. This is where Bayesian backwards reasoning comes in. Now, you need a little more sophistication to do that one. And right now, given this kind of reasoning, there is no way. If you conclude it backwards, it will be like if P then Q, Q therefore P, which is fallacious. But there are conditions, if you get some more information and certain other kinds of things, you can do that. But I'm not going to do that right now. Second. Okay.
Similar one.
Were you also talking about Bayesian?
Yes.
Okay. Mother. Okay. All right. This is now classical deduction, probabilistic and non-probabilistic. Now, let me go on to induction. So suppose you say every human in our sample, representative sample and so on, sample has a heart on the left. This is what we have found in the sample. We have checked everybody. Now what about the population? Okay, therefore, humans have, all humans have heart on the left. So this is induction. From sample to population, the reverse of this case. Now there is a slight problem with this because this is not legitimate, because the fact that the sample has such and such property does not legitimize the case that in every case it should be so. In fact, in this particular case, the conclusion that it is true about the population is simply false. Even if you take 10,000 humans, random sample, and you found that in every case they have heart on the left, we know independently that 1 out of 16,000 has heart on the right. So this is, and you may not find that in the sample. This is the case that Jayashree was talking about. No matter how large your sample, you cannot make a completely certain conclusion about the population. That certainty is not legitimate. So what do? Because we may have to make conclusions about this kind. Because take for example, every human being has exactly one heart. How did we arrive at this? Through this, right? And right now, are we justified in believing that every human being has exactly one heart? That there are no two-heart human beings? Well, we are. But the form is illegitimate. We have to say, we have to indicate our uncertainty. What we do in this case is, until we find evidence to the contrary. It is reasonable to believe that all human beings have heart on the right. And when we find a counterexample, we change our belief. That flag is crucial for this type of reasoning. And notice what I have done is I am admitting the possibility that I could be wrong, and I'm willing to correct myself. This is defeasible in the sense your belief can be defeated, can be proved wrong, and you're saying that is a case, but until I get to that state, it's okay to continue to do so. This will be defeasible induction. And we use it in a huge number of cases. Many of our beliefs about the world are of this type. Even though we don't normally say, until we find contrary evidence, we will do so. That is not articulated, but if you are careful, we should do so. And why is it important to do that? Because then every time you use this phrase, students are aware of the uncertainty of the conclusion. It is not a conclusion written in stone, unlike the other one. That conclusion, that form of reasoning is not allowed in mathematics, because math demands later certainty. That's the reason. It is okay in science. You look a little perplexed.
Yeah, so I wanted to ask, how is it different from probabilistic reasoning? Because here also we have a probability that a person can be having 11 fingers, and here also we have.
Because I did not use expressions like that. I am not stating a probability. I'm saying, yeah. But then I know that there's a problem, so I'm saying I'm willing to admit I could be wrong. Because notice that once you have that, once you have concluded that all human beings have heart on the left, it allows me to do the deductive reasoning. Right? Of course, all those cases of deductive reasoning are based on inductive defeasible reasoning, and so there's a possibility we could be wrong. But that's not at this stage. Now, there is an alternative. You could say every human being, I'm going to write the same thing, every human being in the sample has heart on the left. Suppose I don't want to assert this one. There is an alternative, namely, therefore, it is highly probable that all human beings have heart on the left. Now, you are not stating the probability of your being wrong, you are being cautious, and I don't want to be wrong, so I will kind of play it safe. This one is risky, because you may have to say you were wrong. This one is not risky, this is just cautious.
I'm hearing this talking.
Singing now.
Bhagish, this is still talking.
Ghost in the machine.
Strange machine. And the funny thing is me.
So Mohan's talking to Mohan.
Yeah.
Probability
And
increases with
the other thing, this is not really that technology is. Okay, so this would be probabilistic induction. And these two options are allowed to us. Now, the difficulty with this is this. One would expect, notice that you can replace this with a number. Right? Instead of saying highly probable, you could ask, what is the probability? And one would expect that statistics, which is really a form of reasoning from sample to population, would give us that number. I will not go into the details, but the rules of standard error in stats, if you have this situation, will force you to conclude that there is no possibility of error, so the certainty is 100%. You cannot use stats in that situation. And the stats that allows you a probability doesn't exist yet. I have asked many statisticians, can you give me a mechanism to calculate the probability? There should be a way. I can sketch the way, but I don't know the actual formula. So I leave it in qualitative terms without specifying the number. Yeah.
This would be probabilistic or non-defeasible?
The lower one is probabilistic, It is not defeasible because if you specify the range of error, then it is not defeasible. Right?
But only if you specify the range of error, it becomes non-defeasible.
Yeah. And if you just say highly probable,
It is still defeasible.
it is non-defeasible, but you don't know what this word means. We know it is more than 50%. We know it is less than 100%, but we don't know exactly what range. So it's kind of too vague. That's the only problem.
So it is still non-defeasible.
It is still not feasible because you have played it safe so that you do not lend yourself to errors. That's all. So these are two options when we have sample to population reasoning. Yeah.
If this humans have 10 fingers, if we rearrange this as most humans have 10 fingers, Z has 10 fingers, so Z is likely to be human, provided until we find evidence to the contrary. Then is it
Why don't we wait for Bayesian reasoning? It's much better for that. Instead of doing all these things, you have to look at certain other facts to go backwards.
What does the word defeasible mean?
Defeatable. Something, a conclusion that can be defeated. That's what it means.
Actually, in the last one, it is by nature a defeasible argument, but inserting a word, you have converted it into a non-defeasible.
Yeah, the situation is defeasible,
Right.
but since I have formulated my conclusion in careful way, I have escaped from being defeated.
But is it all not wordsmithing?
No, it's the attitude. Here, I'm taking a risk in being wrong. Here, I'm not taking a risk in being wrong. And a great deal of scientific inquiry takes that risk in theory construction. So
it
it's
is
your
the
choice.
Attitude you mean? That
Yeah.
I'm willing to. I think about it.
Yeah. It's like sticking your neck out and say, I know that you can find data to kill me. Go find out the data. That takes you to a different line of research. Here, you're not going to look for counterexamples. Here, on the other hand, you'll be constantly in search for counterexamples.
So I was going to say, if you say defeatable as can be shown to be false.
Right.
And if you think of the sticking your neck out thing as awareness of fallibility, the attitude of awareness of fallibility. Which is a central characteristic of
Yeah.
science.
Here, on the other hand,
Non-defeasible.
so in stats, you talk about confidence interval and so on.
Instead of less confident, can it be a qualitative statement rather than quantitative? The
Which one?
highly probable, the second one, where you
Yeah.
written less confident.
Highly probable is less confident.
Yes, so it's
You
a
know, even if
qualitative
you give a
statement.
number, it is still less confident.
Yes.
Whereas the other one is not. It's a confidence combined with a sense of fallibility. That's a peculiar state, but that's exactly what you have in
But
science.
that's more for social science,
Which one?
the lower one.
Not really. No. There's a lot of probabilistic stuff even in physics. And there is also a lot of social, so-called, well, to begin with, I don't know what one means by social science. The kind of science that we practice, Tara and I, is linguistics, which could be treated as social, but we have no idea why it is called social. It is not social. And it doesn't use stats. It uses that form of reasoning. Yeah, so it's like
How you classify?
the classification of knowledge that is given in schools and colleges is completely incoherent. It's very difficult to make sense of that classification.
Highly defeasible.
No, it's wrong. Nonsense. Defeasible, it should be scrapped. Okay. All right. Now there is a form of reasoning. So I sketched defeasible induction and probabilistic induction. What about defeasible deduction?
Yeah.
Okay. And this is important for moral reasoning. In fact, all moral reasoning is necessarily, it involves from the moral theory to the prediction, it involves conflict resolution, and conflict resolution requires defeasible logic. Suppose I say that Zeno, this is my favorite example, so I'm going to use it again and again in all cases because it's so cute. So Zeno goes to his office every weekday, and 17th January 1999 was a weekday. You will conclude, obviously, given these two propositions, you will conclude, therefore, Zeno went to his office. That's classical deduction.
Highly probable.
No, given these two propositions, this is the only conclusion. This is classical deduction. Classical deduction doesn't care about probability. Had I said Zeno goes to his office most weekdays, that's just different. That's not what I'm saying. I'm saying every day. Now you say,
Just one. Then we are having some assumptions also. Means he's alive.
I'm just giving you premises. I'm not talking about the states of affairs in the world.
But he's alive, that is an assumption.
It doesn't matter. I could replace these sentences with alphas and betas. Of course, you are assuming that Zeno is a human being. I don't need that assumption, actually. I can state all this purely in terms of alpha and beta in algebraic terms, which makes no reference to the world. And the reasoning would remain the same. So I'm giving this in ordinary English words, but I could also do this in algebraic terms. So instead of saying all humans are mortal, I could say something like, for all x, okay, you say, if x is a human being, human x, then mortal x. This is the way you write all human beings are mortal in predicate calculus. Notice that I'm not saying anything about humans, I'm just saying x. You can plug in anything, any x here, the statement will remain, and the formal logic doesn't care about what you plug in. So I didn't introduce the formal part because I needed to get a feel for the reasoning, and we can go on to the formal aspects of these things a little later. But I'm not introducing rules of inference. The mistake that I made in the earlier document was everything was put in right at the beginning, and people found it so forbidding. So I'm avoiding formalism very carefully. Anyway, those aspects of the beliefs about the world do not come in here. We have to separate beliefs about the world. We're talking about rules of reasoning. Supposing I say, did I make that clear? What I said, did that make sense to you? Okay. Supposing I say, Zeno does not go to his office when he is sick. And on 17th January 1999, Zeno was sick. Now, ignore this part for now. If you are told this, what is the conclusion? You will say, on 17th January, Zeno did not go. Right? If this is all that is given, that's your conclusion. In classical logic, if you are given this and this, what will be conclusion? Zeno went to his office and Zeno didn't go to his office. That's a logical contradiction. That's what we mean by conflict. When two propositions are logically contradictory, we may say they are in conflict. How do you resolve the conflict? In classical logic, you do get a logical contradiction. There is no way of avoiding it. Therefore, you cannot put together these four statements in the same body of knowledge. That would mean a logical contradiction. Therefore, you can't do that. But we play with this kind of stuff all the time, in real life and in many academic domains. What's the way to take care of this? The way to take care of this is to have a system of logic in which when there is a contradiction, so such as you conclude P is true and P is not true, you pick one of them, okay, and reject the other. So one way of doing this is to say that this is proposition 1 and this is proposition 2, and you can say when there is a conflict, 2 is prior to 1. So 2 wins. Now you can say the conclusion is Zeno didn't go to his office. This one loses out. That is a logic of prioritization or a logic of ranking and so on. You could put many such principles. What you're doing is arranging them in their order of priority, and the higher one wins in a conflict.
How is the priority decided?
You decide. This is like saying how do you decide the value of a constant in some law, scientific law. You play around, decide what you want. That's how it is.
Where does defeasibility come in here?
Yes?
Where does defeasibility come in here? Why we call this as defeasible reduction?
Yes. If you have 2 is prior to 1, 1 is defeated. So this conclusion that Zeno went to his office is defeated by the other one because that has priority. The stronger one wins. The weaker one is defeated. That's a way of saying. Okay, that means that the weaker one is rejected.
So if we change that, Zeno goes to the office every weekday provided he is not sick.
You could, but then you will make your premises too complicated. There are many, notice that our goal is to state very simple laws and get the predictions through the interaction. And if you put in all these details into the laws themselves, that is what lawyers do, then the law will run into about a few thousand pages. Instead, what we are trying to do here is state the laws in a simplest possible way and get the complexities of the actual situation from their interaction. That's a strategy we are using here.
That could be a prediction then. As a result of the
Yeah.
prioritization that we've done, we can
Yeah.
say that Zeno goes
Exactly.
to office every weekend.
You will get the
unless-
prediction either way.
Yeah.
If you choose the lawyer's approach, you complicate the theory and get the prediction. If you use the scientist's approach, you use a simpler statement of laws and still get the prediction from interactions.
This is what we were doing that day with the moral principles.
Yeah,
Simple
exactly.
statements and their combinations or interactions will
Will give you the, yeah, exactly, precisely. So moral reasoning is necessarily defeasible. There is another way of doing it. Instead of using ranking, you can just specify the strength. So for example, I could say that law number 1 has a strength of 0.5 and law number 2 has a strength of 0.6. Now the rule of the logic says the stronger conclusion wins. You'll get the same result. The advantage of saying stronger is that there are interactions that you cannot get from ranking that you can get from this. I'm not going to go into the details. Yeah.
When we are doing deduction, we have the thing that the grounds of deduction are true.
Sorry?
Our premises are true.
Premises are true, absolutely.
But in this case, if these two cannot both be true, Zeno goes to office every weekday.
Exactly.
And Zeno does not, so they cannot both be true.
Yes.
So is it okay to have all four as premises?
Yes. In diffusible logic, it is perfectly okay. It doesn't lead to a contradiction.
Actually, if you think of it as
This is strange for mathematicians. I know, because in mathematics you will say this is an inconsistent system.
Yeah.
In science, we avoid the inconsistency by specifying the degree of strength and moving from non-diffusible logic to diffusible logic. Yeah.
this is because mathematicians live in a different world. In science, if you put diffeasible reasoning as you get further information, your conclusion can change.
Yeah.
That's actually the substance of it.
Yeah. Notice that in mathematics, once you prove a theorem, it can never be unproved. In science, you prove a theory, it can easily be unproved. That's the nature of scientific inquiry.
Okay, now what you said that day about being monotonic and non-monotonic is fitting in.
Yeah, okay. What? All right. Let me write this down, what the history said. Okay, I'm not going to discuss this. Those of you who have a reasonably high tolerance for formal stuff can do a Google search. This is the technical term, and there are formal rules for non-monotonic reasoning. This was discovered in the 50s. And one person who did this, developed this, was John McCarthy. An artificial intelligence person who discovered that for reasoning in ordinary life, you cannot use Aristotelian reasoning. And the standard mathematical reasoning embedded in things like propositional calculus and predicate calculus. These are all formal matters. You will not find words there, you will find symbols, algebraic symbols. So if you have some degree of tolerance for algebraic symbols, go there. A great deal of work has been done on this kind of stuff in the Center for the Study of Language and Information, Stanford. So go to the Stanford Encyclopedia of Philosophy and do a search for non-monotonic reasoning. You will find enough for 6 months or more. Okay, so this is the baby version of what logicians do, what I've given in a small tablet form. And the small tablet form is enough for school students. In fact, for school students, even the tablet may not be digestible. I guess about by 15, 16 it is digestible if you do this early enough. I mean, if you begin reasoning at the age of 10 or 12, then this is digestible. Otherwise, it's terribly confusing. This kind of, I've done only 2 of them, but what happens when you have a cluster of propositions? How do you calculate?
Can't
So
you
in
assign various
math-
strengths?
Pardon me?
Can't you assign various strengths for each?
Yes, you can, but now you have to have some condition for combining. For example, suppose you have something like this. Zeno, when there is an emergency, Zeno goes to his office. Now notice that these two, and if you say that on that day there was an emergency, these 2 things will conclude that Zeno goes to his office. This one will say Zeno does not go to his office. You can calculate this by using strengths. So number 3, you can say 0.3. If you add up, 5 and 3 will give you 8, and this one would win. But now I am assuming that the interaction is purely additive. Suppose it is not. And it should not be, because there are cases, extremely interesting cases that you find. For example, in agreement, No, I'm not going to talk about that. In order to make correct predictions of Hindi agreement, subject-verb agreement, you need to use a reasoning of this kind, and that has extremely interesting properties, which cannot be done additively. You need a different way of calculating it, and those are the kinds of things that logicians do. So what I've given is a very simplified version. In actual cases, you need to make it more sophisticated. If you want to mimic human reasoning, which you need to do. Also not simply human reasoning, but also various aspects of mind and brain. Okay, I think that, yeah.
About the same example, despite these three conclusions that we have arrived at, there may be a fourth situation where he's so sick that he cannot go.
Yeah.
So can my conclusion then say it is most likely, given 1 and 3, it is, can we use probabilistic?
You don't need, if you have feasibility, you don't need probability. What you need to do is to assign strength depending upon the degree of sickness. So this one would increase if this increases. So if Zeno has a mild headache, Zeno will still go to a headache. So Zeno will still go to his office.
But if he's
if he has an
unconscious
appendicitis or whatever inflammation, then he wouldn't. So that's a question of using things like this to assign strength or rearrange strength. The strength assignment will do it. You don't need probability.
Since it's dealing with, say, I mean, in this situation, or even in, say, moral principles,
Yeah.
it is dealing with human beings,
Yeah.
one would still maybe go against, I don't know, is it possible that they would still do something outside of the framework of reasoning, and so is it?
What humans do rationally is here. There are also bases for action which are not rational. All right. So, for example, if so imagine the following scenario: a bunch of this is an example that I give to my students. A bunch of gangsters come in and they tie up all of us. They tie up me too, and give me a gun. Okay, and they say, okay, shoot one of these people at random. If you don't, we'll shoot whatever, either all of them or 49 of them. Leave one person free. Okay, rationally, what should I do? I should shoot one of you, right? And I will, that's what I ought to do, and I might do that, and I might, after that, I might be eternally depressed, or I might commit suicide, whatever, but this is my rational responsibility. Now, imagine that sitting amongst you is my daughter, and the guys say, either kill your daughter, or we will kill everybody except your daughter. Now, my rational moral principles say that I should kill my daughter to save the lives of all of you. Do you think I will do that? No way, right? But that is not on the basis of moral consideration. It is purely self-interest.
Or emotional.
No, self-interest comes into conflict with morality, and you have to decide how much of self-interest and how much of morality. Morality says other interest is more important than self-interest. But I have, my attachment to myself is much greater, so I may not consider morality at that point. And this happens in human life all the time. You have to choose between these two. They are also in conflict, morality and self-interest. Some people have greater tolerance for suppressing self-interest and working for other interests. Some people have, different. We are just different people, that's all. Other questions?
And one look forward to this reasoning in case of for conflict resolution in real life.
The kind of conflict that you may have in mind is really conflict between self-interest.
Yeah, conflict between two ideas.
Two ideas, propositions.
Yeah.
Yes. If you are thinking about, for example, the conflict between two theories in physics, this is okay. But if there is a conflict between two businessmen, you can't use this.
Arguments, but let's say there are two ideas and they are conflicting and you're not able to
Yeah.
make a rational decision.
You could use, in fact, in science, systematically, this is what is used. In choosing between theories, when theories are defeated, this is the underlying logic.
What was strength on a given day suddenly became weakness.
So is this for, sorry,
A, in math, then we don't have a feasible.
No. That is why there are no debates in mathematics. Once a theorem is proved, that's it. It is proved forever. In science, when a theory is proved, there could be some other theory competing with it, and you have a debate. Debates quite often involve this, and not quite often, quite often. No, I cannot think of a debate without this. And math doesn't, mathematical proofs do not lend themselves to debates.
Like you said, conflicts, say
Yeah.
Indo-Pak conflict.
Is that an emotional conflict or is that
That's
a...
what.
I'm describing conflict between propositions, not conflicts between people.
So internal conflicts.
Yeah, that conflict is different.
No, internal conflicts again will be self-interest and.
It can be a between
So
two
that cannot
choices
be-
also, no?
Choices, yeah, now you remove the person
Huh.
and you just have propositions.
Yeah, exactly. But it's mostly for conflicts within the self, not between two people. If we
When you say
have-
within the within the same person, yeah, right,
that's
right.
what I meant.
Yeah. So I need to decide which conclusion is true. There is no emotional problem here. I rationally decide which proposition is true. But sometimes these propositions create emotional problems. That's a different kind of conflict.
Outside of the rational.
Yeah. To do this, you have to assume that people do not exist. They're only propositions. That's easy for some people.
That degree of detachment is probably what would help in a lot of situations.
Actually, that could happen
Eh?
even with this very case. So, Zeno is sick
Yeah,
and there is an emergency.
yeah.
Zeno